Good morning, ma'am. Good morning, classmates. At this juncture, we will explain to you the photoelectric effect and relativity, the special theory of relativity. The proponent of this concept is none other than the genius of all time, Albert Einstein. He explained the photoelectric effect in 1905, for which he received the Nobel Prize in Physics in 1921. As for the special theory of relativity, also formulated in 1905, his theory revolutionized the understanding of space, time, and the relationship between matter and energy. The photoelectric effect refers to the emission of electrons from a material surface when exposed to light. Classical wave theories couldn't explain the observed phenomena, prompting the need for a new theory.
Now let's delve into the world of classical physics versus quantum physics. Classical physics developed over centuries by luminaries like Newton and Maxwell provide a macroscopic understanding of the physical world. Governed by deterministic laws, it effectively describes the motion of everyday objects and the behavior of large-scale systems. For probing extreme conditions, classical physics encounters limitations. Quantum physics, born in the early 20th century, revolutionized our understanding of the subatomic world. It introduces principles like wave particles, duality, and uncertainty principle. Acknowledging the probabilistic nature of particles at the quantum level, unlike classical physics, quantum mechanics drives describing phenomena on an atomic and subatomic scale, challenging classical institutions with concepts such as superposition and entanglement. While classical physics remains powerful in our day-to-day experience, quantum physics unravels the complexities of the very small, pushes the boundaries of our comprehension of the fundamental nature of reality. The coexistence and complementarity of these two branches exemplify the dual nature of the physical universe.
When light strikes at a certain light-sensitive material, it may cause it to give up electrons. While in the concept of photoelectric effect, high-frequency light from a dim source can eject electrons from a photosensitive material. While in low-frequency light, even when it comes to the brightest light, it cannot eject electrons. In summary, light, like all other radiation, is made up of small particles called photons. The higher frequency, the more energy the photons have. Einstein stated that light interacts with matter as a stream of particle-like photons.
So, good morning everyone. I'm going to discuss about the photoelectric effect. But to be precise, I'm going to read what is the photoelectric effect. So number one, if a photon hits an atom of a certain material, it may be absorbed by an electron of that material. Number two, however, if a photon has enough energy, the electron is ejected or emitted from the atom. And the last is, in this way, light energy changes into electrical energy. That is the concept of the photoelectric effect. I will give you an example to make it clear. The solar power plants. Right now, most of us are using the solar technology. The appliances, the tools, our daily living is controlled by solar energy for those people that can afford to buy solar panels. So how does it work? Those light energy, once it enters some materials that has a photoemittive characteristic, the light will be absorbed by the electron of an atom. However, according to the photoelectric effect, if that material already reaches its limit and has enough energy, those light that is absorbed will be released or ejected from the atom. In that way, those released energy will become the electrical energy. So from light energy, we will have the electrical energy once those light energy absorbed by the atom will be emitted once it has exceeded its limit. So the next one, we will have the example. If wires are attached to a photoelectric material, the electrons can flow along the wires, forming an electric current. So, based sa sinabi ko kanina, ganun pa rin, if a wire has a photoemitting material, then a light already hit the photoemitting material, the atom of that material will absorb the light. But according to the photoelectric effect, I will repeat it once again, if that already exceeded its limit, those light energy will become electric energy. Then why is the photoelectric effect so important? First of all, it explains the particle nature of light. The next one is, it is the basis of the quantum theory that will be discussed in the other group, and it is used in photocells, solar calculators, alarms, automatic garage, door openers, flash of a camera. So yun nga, this is also connected to the solar panels, to the solar power plants. Aside from light bulbs, from electric fans to electrical appliances at home, we also have several usage of the solar power plants or the solar power. We have the photocells, the solar calculators, the alarms, automatic garage, door openers, and the flash of camera. We now have the idea that energy or electrical energy doesn't always come from hydropower plants and from gas or the consumption of gas. We also have that photons or the light energy.
Now, let us have an example concept of photoelectric effect in real life. So, the photoelectric effect can be observed in everyday items like solar panels. These are the electrons. When the sunlight hits the surface, it causes the electrons to be emitted. And it generates energy. This phenomenon is crucial for renewable energy systems.
For another example is in digital cameras or the cameras of your phone. The photoelectric effect is the fundamental process by which the sensor converts incoming light into digital information. It comprises numerous tiny light-sensitive elements called pixels. When light consisting of photons, these pixels transfer its energy to electron within the pixels. This marks the beginning of photoelectric effect. The sensor translates this electrical signal into digital data. This data forms the basis for creating the image captured by the digital camera. When you take a picture, this process swiftly translates the received light into digital image containing details and colors corresponding to the received from the captured scene.
Okay, for now, let us have another example of the photoelectric effect that can be observed in real-life scenario o sa ating pang-araw-araw na buhay. A perfect example of that is yung kapag napunta tayo sa groceries at kapag nagpapacheck tayo ng price or kapag magpapabayad na. That is none other than yung paggamit natin ng barcode scanner. So alam naman natin na sa barcode scanner ay meron siyang light source of course. Siya yung produce ng light na LED papunta dun sa ating barcode. At dun sa barcode, ang distinctive features niya ay meron siya mga pattern ng mga white at black and white. So yung black part, sila yung part na nag-absorb ng light na binibigay nitong barcode scanner natin. And yung white part ng barcode, siya naman yung nagre-reflect ng liwanag mo, nagagaling kay LEDs ng ating scanner. So itong ating scanner, meron siyang photodiode sa loob. Siya yung nag-i-interpret kung ano ang ginagawa nitong barcode na to, kung siya ba'y mag-absorb or mag-reflect ng liwanag. And after na ma-release yung liwanag from the barcode, so pupunta siya dito, malalaman na ni photodiode na nasa loob nitong ating scanner kung ano yung pattern or information na meron dito sa barcode na to. So itong ating scanner, nakakonect siya sa isang computer. So once na makumpleto yung process nito,
at malaman kung aling part yung nag-absorb ng light and which part does not absorb light or reflect, malalaman na natin yung pricing directly from the computer that is attached to the scanner itself. So that is how simple lang. So the scanner releases light and the barcode either absorbs or reflects the light, and the photodiode inside the scanner will interpret the information from the barcode itself. And after that, it will be reflected to the monitor and we will know kung magkano or ano yung laman ng barcode na ating binigay sa isang product that will be taken.
Einstein began with two postulates. The first concerns with frame of reference. When we say something is moving, we mean that the position is relative to something else, or the frame of reference is changing. In the theory of relativity, frames of reference are essential concept. Special relativity formulated by Albert Einstein in the 1905. Introduced that the idea of space and time are intertwined in four-dimensional continuum known as space-time. Observers in different inertial frames of reference moving at constant velocities relative to each other may perceive events differently. The theory emphasizes the relativity of simultaneity and time dilation, stating that two events that appear simultaneous to one observer may not be the simultaneous for one moving observer. This challenges classical notion of absolute and time. General relativity, developed by Einstein in the 1950s, extends these ideas to include gravity, gravity is not seen as a force but as the curvature of space-time caused by mass and energy. In this theory, frame of reference are no longer limited to inertial motion. They can be accelerated motion within gravitational fields. In essence, the theory of relativity reshapes the understanding of space, time, and motion by highlighting the relative nature of this concept across the different frames of reference.
Example of adding velocities. You're on the top of traveling 60 miles an hour. Relative to your position or from your perspective, the train is not moving and neither are you. You throw a ball in the direction of the train at 15 miles an hour. From your perspectives, the ball is only moving at 15 miles an hour. A person standing on the both sides of the tracks watches the train go by. They see it move at 60 miles an hour. They watch you throw the ball in the direction of the train. However, they see you throw the ball at 70 miles an hour.
Now, to explain the relativity of light, let's use the same train example. Since the speed of light is 186,000 miles per second, then let's just say that the train is moving at half speed or 93,000 miles per second. What happens if you turn a flashlight on? What does the observer see? Assuming that they can see or observe the speed of light with their eyes, do they see the velocity or the speed of the train in addition to the speed in light? In other words, do they take the speed of the train or 93,000 miles per second and the speed of light 186,000 miles per second and combine them getting 279 miles per second like what we did when we threw the ball? If you answered yes, then you are wrong. What if you turn the flashlight on while riding the train? What is the speed of the light in the flashlight relative to you? Or from your perspective? Is it 186,000 miles per second or the speed of light? If you answered yes, then you're right. Wait a minute. Should light be relative to whoever is observing it, like when we threw the ball? Albert Einstein said, that the speed of light is always the same no matter who is observing it. Einstein's statement means that if you have two observers in relative motion to each other and both measure the speed of light, they will both find that the speed of light is approximately 299,792 kilometers per second, or about 186,282 miles per second, regardless of the motion of the source or light of the observer. This constancy of the speed of light is in contrast to classical Newtonian physics, wherein velocities typically add or subtract depending on the motion of the observer and the source. Special relativity, with its invariance of the speed of light, led to profound changes in our understanding of space and time, introducing concepts like time dilation and length contraction, which have been experimentally verified in various ways over the years.